previous lecture we talked about what is going on inside the core of the sun, how nuclear fusion is taking place and how hydrogen is being converted into helium. So, we saw that the temperatures are about 1.4 into 10 to the power 7 K and so at these temperatures in the core, and the density is also very high, density of that hydrogen core around 160 grams per centimeter cube and corresponding pressure, and with that the reactions PP1, then PP2, PP3, the main reactions, and the result of all this is that 4 hydrogen nuclei get converted into 4 helium nucleus, and you have 2 positrons and these neutrinos formed, and plus energy of course. Same is the case with the CNO cycle, same final result. This happens around say 2% of the time, and this happens about 98% of the times, and of this this is 85%, this is almost 15%, and this is 0.1%. The neutrinos which come out of these reactions, these neutrinos have different energies in different cycles PP1, PP2, PP3, CNO, etc. And these neutrinos in fact give us an almost live update of what is going on inside the core of the sun with an 8 minutes of delay, because the photons that are created or energy that is created in fusion, that takes long time to come to the surface and get emitted to the earth and other surrounding space, but neutrinos which are produced in these fusion reactions, they almost without interacting with the material, they come out with almost the same speed as the speed of light, and therefore, by studying these neutrinos we know the details of these fusion reactions. Now, today's topic is making of newer elements inside this these stars. Here helium is being made from hydrogen. So, one element is getting converted into another element, and in the sun itself, if we see apart from this hydrogen and helium, we have varieties of other elements, some 64 other elements have been detected. And if we look for the whole universe, in the whole universe you have some 100 odd elements, some 94 elements or so stable elements that we know in periodic table. And if we think of the stable nuclei, there are about 300 of them stable nuclei, starting from this hydrogen, helium, then carbon, nitrogen, oxygen, everything, boron, everything. So many nuclei, this iron and silicon and zirconium and everything. So, where these nuclei were formed for the first time, so that is known as nucleosynthesis, and it turns out that you can think of 2 parts. One part where it's called Big Bang nucleosynthesis. You know, the universe is now almost certain that it has started from a big explosion from a point. The entire universe, the entire energy, the entire matter, everything was first confined into a point, and then some explosion took place some 15 billion years ago, which is known as Big Bang, and that is supposedly the beginning of universe, the beginning of space time. No space, no time existed before this event. That is how people describe this. and from there, from the Big Bang, that after the explosion, universe started expanding. So, within first few minutes, lots of complex events took place, and these protons and neutrons and neutrinos and photons and these things were created. Initially the temperatures were very high, so that no bound system could be can be thought of. So, at those temperatures it was all quarks and other things, but when the temperature came down, then these quarks got into the bound states, making protons, making neutrons, and there were so many theories and speculations and calculations to describe those early part, that early part of just after the Big Bang. But within few minutes, the situation was such, the temperatures were such that bound systems could exist, number one. Number two, protons could combine into somewhat heavier nuclei like deuteron, and from there helium 3, and from there helium 4, and so on. But within minutes the temperature fell down because of this expansion. So, so that the nucleosynthesis, the nuclear fusion, making of heavier nuclei from lighter nuclei, that process could not be sustained anymore, and that ends the Big Bang nucleosynthesis. So, what was the composition of the universe after that? Now, our theories and our calculations have are showing that the mostly it was by weight about 75% of hydrogen and 25% of helium. 74 point something and 24 point something and so on, and in the rest 1% you had this little bit of lithium, little bit of perhaps boron and so on. That is all. After that nothing. So, nothing beyond A equal to 7 lithium was synthesized there, and that makes what we called primordial composition of the universe. So, the matter was in this form, hydrogen and helium almost 75%, 25% by weight, and trace amount of one or two other material. That is the composition of the universe as such. This is first few minutes, and then from there onwards till now 15 billion years, this primary material which is there in the space, at places they condense in galaxies, in stars, and in the stars nuclear fusion takes place, and all those other elements, they are formed inside these stars, just as hydrogen is fusing into helium. So, there are so many stars, some hundreds of billions of galaxies and hundreds of billions of stars in the galaxy. So, and the stars are of various sizes, and depending on the size some particular nuclei could be synthesized inside the core of that. So, first let us look at the total abundance of different nuclei in the universe. So, let look at your screens. I will show you an abundance graph, the different nuclei and their abundance. Okay, so, on your screen you have this periodic table, which shows that there are so many elements different, and each element has a different Z and corresponding N. For each Z you can have more than one stable nuclei isotopes. So, around 300 of stable nuclei, and this is the abundance diagram. So, you can see that the most abundant element is here, and that is hydrogen. Remember, when you read 8 here, it is 10 to the power 8. If it is 10, it is 10 to the power 10, and so on. So, it is log of log scale, and on this side it is Z. What is the next? The next is helium. This is helium. Z is equal to 2. And after that, what is next? Next is this. So, this is carbon. this was helium, this was hydrogen, and this is carbon. And in between helium and carbon, Z is equal to 3, lithium is here, Z is equal to 4, beryllium is here, Z is equal to 5, boron is here. So, they have very small concentrations in the universe, and after that you have carbon. After carbon it will be nitrogen here, after nitrogen it will be oxygen here, after oxygen it will be 9. So, fluorine here and so on, neon here. So, increase Z in steps of 1 and you get this diagram. Now, there are several things which I should point out looking at this diagram. One is hydrogen is by far most abundant material, and even today after so many 15 billions of years of stars making newer elements, its composition, its weight percentage still remains very close to 75. And next is helium, that also remains very close to that 25. So, all these 15 billion years of synthesis of helium and other elements has given only a very minute change in the composition of the universe, what it was just 3 minutes after or 4 minutes after or few minutes after this big bang. So, that is one. Hydrogen and helium are still almost 99% of the universe is hydrogen and helium. Another thing I would point out, this oscillations, the points you are seeing are in steps of Z is equal to 1. So, as you increase Z in steps of 1, you can see the abundance goes up and down, then up and then down, then up and then down. So, all the even Z materials, this helium and then carbon and then oxygen and then neon and then magnesium and then silicon, all these even Z materials are here, they are here. So, even Z materials have a higher abundance than the next odd Z material. So, this going up and down, this oscillation, that is one thing which you can identify from this. The other thing you can identify somewhere here, this is Z is equal to 26, this is Z is equal to 26 and that is iron. 56 iron, Z is equal to 26 and is equal to 30. Here in this after this helium and hydrogen and carbon, oxygen, etc., in this vicinity this has highest abundance, and once you look at the elements which are away from this iron, Z is equal to 30 onwards, this abundance is much smaller than the first part. So, you can see this as two different parts. Okay. This whole diagram you can see abundance wise, this is the 0 line. 0 line means, remember, it is a log scale. So, all this part is less than that 0 line and all this part is more than 0 line. So, somewhere this iron, nickel, that region where A is 56 and around that, it is some kind of a dividing line. Below that abundance is high, more than that abundance suddenly drops. So, that is one another observation you can see. And in general as you increase this, if you go towards heavier and heavier nuclei, you can see that abundance gradually goes down. I can show the expanded version of this abundance diagram for lighter elements, and that is on this next slide, and that is here. So, here you can see more clearly what happens in that first part of it. Hydrogen is here and then you have helium and so on, this is lithium, then beryllium, then boron, here this is carbon, this is carbon, this is then nitrogen, and this is oxygen, right, and so on. This will be fluorine, and so this way. So, you can look at this diagram and see how, apart from the initial things, hydrogen and helium and very low abundance of this lithium, beryllium and boron, these have some special meanings, and after that in general you can see that as you are going towards heavier things, the abundance is going down, the fluctuations you can see going up and down, and here is that iron part, Z is equal to 26, N is equal to 30, that is somewhere here, and then after the sudden drop, all these things you can see from here. Okay. So, let me come to the board. So, that was the kind of abundance that was displayed on this graph. How scientists know about that? They have all varieties of spectroscopy, all varieties of radiations that is coming from different portions of the space that they analyze, and from that they derive all these informations. And once this information is there, then the theories, the models are built up. So, let us first look at this hydrogen and helium, 74% of 75% roughly of hydrogen and 25% of helium. As I said, most of it was synthesized, most of this was formed during that Big Bang period, within few minutes of that, and after that only small changes are there. Carbon, the third most abundant material is carbon, and carbon is is very important for life. So, all this carbon that has come only through this stellar nuclear synthesis, the fusion, nuclear fusion inside different stars, only there carbon can be formed, because during the Big Bang the situation was not at all allowing formation of carbon. Now, formation of carbon itself is a very interesting thing, because helium is there, hydrogen is there, and the temperatures are high. Hydrogen is converting into helium, that is in our sun and many more stars, and beyond that what happens? Once this hydrogen core gets largely converted into helium, so that there is no more hydrogen to burn or to fuse into helium. After that, the fusion reaction inside that core stops for a while. That will happen in our sun some 5 billion years from now, when the hydrogen supply in the core will be exhausted, and the temperatures are not very high, so that helium can fuse together. Then the fusion will stop for a while, and this core will start shrinking. Why? Because of gravitation. At present also the gravitation is there when the hydrogen is converting into helium, that time also the gravitation is there, which is trying to collapse the core, trying to shrink the core. But then the pressure due to this energy production, the outward pressure, outward forces that are the pressure gradient which is there because of this energy production which is going towards outwards, that balances this gravitational traction, and this is known as hydrostatic equilibrium. Once this fusion stops in the core and no more energy is produced, then the gravitation takes over and then the core shrinks. As the core shrinks, the gravitational potential energy is converted into thermal energy and the temperature rises, and at a certain stage the temperature rises to a value where helium can fuse. Why do you need higher temperature for helium fusion? Because of Coulomb barrier. Hydrogen, Z1, Z2 is 1, helium, Z1, Z2 will be 4. So, you need higher temperatures, and when those temperatures are attained, then helium fusion starts or can start. Now, helium fusion is again a very interesting thing, because if two helium nuclei, two alpha particles 4He plus 4He, if they fuse, if nuclear fusion takes place between these two, what product do you expect? You expect 8 beryllium 4 plus gamma, etc. Now, this is very unlikely, because beryllium 8 is not a stable particle. If you look at the Q value is negative, minus 94 kilo electron volts, and therefore, as soon as this 8 beryllium forms, it decays into 4 He2 plus 4 He2, and the time scales are something like 10 to the minus 16 seconds. So, that is why you do not have 8 beryllium nucleus, it is not a stable nucleus. Okay. So, immediately, almost immediately 10 to the minus 16 minus 17 seconds, at that time scale it converts back into 4 He plus 4 He. And remember, you do not gain energy by this fusion, because helium 4 is an extraordinarily stable particle. The binding energy per nucleon is very high here, and so even though you are going towards higher mass value, you are not gaining anything into energy. So, this reaction is very less probable. And if this reaction does not take place, then nothing else will take place, because it has to start from here. This was a puzzle. This is also known as bottleneck. So, this was a puzzle, but then people realized, scientists realized, that at these high temperatures, even if this beryllium is unstable and it will decay back into 2 alpha particles, but at these high temperatures there could be some thermal equilibrium between 2 alpha particles and 8 beryllium. At higher temperature, you know, the higher energy levels are also populated, right, e to the power minus capital E by kT, that kind of distribution. And since the density, if the densities are very high and this 8 beryllium forms for even a tiny period, 10 to the minus 16 or minus 17 seconds, if the helium concentration around is very high and the temperatures are high, then it is possible that before it decays, it has formed, and then before it decays, it meets another alpha particle, another helium nucleus, and that makes 12 carbon. 12 carbon, it will go into or plus gamma, it can be 12 carbon plus gamma. So, if the concentration of this helium nuclei around is very high, then it is possible, then one can calculate the probabilities that before it decays into 2 alpha particles, it combines with helium, another helium nucleus, and makes 12 carbon. Now, 12 carbon is stable. The ground state 12 carbon as such is stable, but then when it combines, what it forms is carbon 12 in an excited state, because if we just calculate based on this reaction, it turns out that the high abundance of carbon one cannot explain. So, that high percentage, that high concentration of carbon in universe will not come out according to the theories of fusion and the theories of physics. If we just think that whenever this helium combines with this, it will make a carbon, because the production rate will be much small. And to understand how that high concentration of carbon is coming, great scientist Hoyle proposed or predicted that this carbon 12 must have an excited state with energies close to this 3 alpha energies, so that the Q value matches and there is a resonance in reaction. Okay, you remember resonance in reactions. If the initial constituents in a reaction, nuclear reaction, and the final product in the in that reaction, there is a level, so that the energies match, then the probabilities of that reaction enhance many orders higher. So, it was a suggestion from Hoyle that this carbon must have an excited state, and this reaction leads to that excited state through resonance, so that the probabilities are high, and that is why we get that much of carbon. And the calculations was that this energy should be somewhere around 7.3 MeV or so. This is for carbon 12 energy. There should be an energy level somewhere around this value, so that a resonance can take place, so that the cross sections can go very high, and therefore, carbon can be produced in large quantities. This was in 1954, and then experimental search began at Caltech, and in 1957 Fowler and the group found experimentally in laboratory that yes, carbon 12 has an excited state. So, this was the prediction, and then 3 years, this was 1954 and 1957 experimentally found, experimental verification, Fowler and group, somewhere around 7.65 MeV, close to that. So, the resonance reaction takes place and the probabilities are high. But then the actual level, if one calculate what is the total mass energy of these 3 alpha particles, 3 helium nuclei, the starting material, and what is the final rest mass energy plus this excitation energy, final energy of this carbon 12 in the excited state, one finds that it is slightly higher. The energy of this carbon's excited state is the total energy including the rest mass energy is slightly higher than the energy of 3 alpha particles, and therefore, spontaneously it would like to decay back into 3 alpha particles. But then there is a competing process, and the competing process is that excited carbon 12 emits a gamma photon and comes to the ground state, and that probability is say 4 parts in 10,000. If that happens, 4 parts in 10,000, rest of the time it goes into 3 alpha particles. But if it does decay through this gamma emission, then it comes to 12 carbon in ground state with energy very stable and much lower than this 3 alpha particles, and you gain energy. So, all that carbon that we have today on earth, in solar system and in the universe was created through this process, 2 alpha particles going into 8 beryllium, and before that 8 beryllium decays another alpha particle combining with it to give excited state carbon, and that excited state carbon with this small probability of coming down to ground state, the entire carbon that exists had been produced in this particular fashion. So, that is how during this helium fusion state, carbon is produced. Our sun will do this, but it will do it some 5 billion years from now, but many of the stars had done it during this 15 billion years of lifetime of universe and are doing it still. So, that is this helium fusion. What happens if the helium supply in the core is exhausted? Once again the nuclear fusion will stop, once again the core will start contracting and temperature increasing. For our sun or other stars of similar masses or somewhat greater masses also, the total mass is not enough to give energies, gravitational potential energies converting into thermal energies, and to give large enough temperature for this carbon core to go for fusion. Okay. This helium, after this helium burning phase, helium fusion phase, you have mostly carbon and some oxygen also. Once you have this carbon, helium is converting into carbon, there is a lot of helium and carbon is being formed. At that time you can have these kinds of reactions. This carbon and helium nuclei are present there. So, that will make 16 oxygen. Okay. 6 here and 2 here. So, 16 oxygen plus gamma, and 16 oxygen can combine with 2 again 4 helium, and that can give you 8 here, 2 here. So, neon. So, these kinds of reactions can take place depending on what is the temperature and what is the concentration and so on. So, during this helium burning phase, mostly it will be carbon, but some oxygen, some neon can also get produced. Once this helium supply is over and you have largely that carbon core or carbon oxygen core, then once again depending on how much is the mass, it can contract to give a temperature large enough so that this carbon oxygen start fusing, or if the mass is not large, as it is the case with our sun and many more stars in the universe, this fusion is almost off. So, if the fusion is off, then that is all. You have carbon, you have synthesized carbon, you have synthesized oxygen, a little bit of neon perhaps, and it is over. But we do have very heavy elements, and they are formed in stars which were much more massive, and these elements are still being formed in stars which are much more massive. In those stars, what happens? In those stars, this core contracts, this carbon core, carbon oxygen core contracts, temperatures become high, and at a certain stage this carbon nuclei, they start fusing. When carbon nuclei start fusing, what can they produce? Several things. One is that 12 carbon plus 12 carbon can go for 20 neon plus 4 He. It can also go for 24 magnesium, but since alpha particle helium nucleus is very stable, its binding energy per nucleon is very large. So, this reaction is more probable. So, this, and important thing is that you again get this helium nucleus through this reaction. Helium was already consumed and you had only carbon core or oxygen core, carbon oxygen core, but now fresh helium is being produced, and when fresh helium is produced, it starts combining with that. So, all that reaction will keep on going, oxygen and so on. So, with oxygen it will go for neon, with neon it will go for magnesium. So, these kinds of reactions will go on, and this process will keep on going. Once this carbon core, that fuel is exhausted, outside layers other things are going on. If it is carbon core which is giving fusion here, outside that you will have helium layers which will be fusing, and after that you will have hydrogen layer which will be fusing, and after that you have colder hydrogen. So, that will be the structure, and this structure more and more layers will form that the mass of the total star is high. At the end of it you have something like 28 silicon core. So, all this carbon etc., this process will go on from 16 you will go to 20, 20 to 24 and 24 to 28, that is 28 silicon. And now the Coulomb barrier is very high, Coulomb barrier is very high, fusion is becoming more and more difficult. But fortunately the same alpha, production of alpha and absorption of alpha, that process can still go on. If you want to fuse 28 silicon plus 28 silicon, it is very difficult, but that 28 silicon and so many gamma photons are there. So, even that those gamma photons can disintegrate this 28 silicon and create alpha particle. So, at those high temperatures 28 silicon and gamma, lot many gamma photons are there, you have radiation. So, it can disintegrate 24 Mg and plus 4 He, this is 12 and this is 14. And once this 4 He is there, that can combine with 28 silicon. Remember, you have lot of 28 silicon in the core. So, one nucleus combines, gives you one helium nucleus, and this helium nucleus combined with another silicon which is present there. So, 4 He, this will give you sulfur 32S, and similarly this 32S 16. This 32S will combine with 4 He2 and that will give 36 argon and so on. So, this process can go on and ultimately what you get is 56 nickel. Just keep on adding alpha particles are continuously produced there and consumed there. So, you get this 56 nickel, and then this beta decays, in fact twice, once it will go to cobalt and then it will go to iron. 28 here, 27 here and 26 here, and this is that most stable nucleus. So, if the size of the star is quite large, so that it can reach to this position, to this state, then this 56 iron can be produced as the end product, kind of end product, nickel, some nickel, some iron and so on. And after that, once for all, the nuclear fusion has stopped in the star. So, up to this iron nickel state, which the first part on that abundance diagram, so that is created in this fashion. Now, this is the main process of nuclear fusion in the stars, and all these elements which are there, they have even Z, and therefore, the concentration, the abundance of these even Z elements are higher than the odd Z elements in their neighborhood, because this is the main process with which the elements are being produced, new nuclei are being produced. Then how that those odd Z nuclei are produced? They are produced in some kind of stray reactions that take place here and there. So, I will show you it on the screen what kind of reactions take place when you have these main things are going on in the side. Once in a while some other reactions take place, giving you an odd value of Z. Look at your screen. Yeah, so can see here this carbon plus carbon, normally it should go for 24 magnesium, but it does go sometimes 23 sodium plus proton. So, 23 sodium. Z is equal to 23 sodium is Z is equal to 11 and this is 12. A constituent of our common salt is produced in this fashion. Similarly, 20 neon plus 4 He, that gives 23 sodium once again and then plus a proton. Here 16O plus 16O, 32 sulfur is the normal thing which you can expect, but you also have 31 phosphorus plus this proton. So, this way this phosphorus is produced. 12 carbon, this is right in the helium burning phase, 12 carbon, or even in hydrogen burning phase, if you have the CNO cycle going on, this 12 carbon taking one proton going to 13 this nitrogen and that decaying to 13 carbon and then that combining with proton to give you 14 nitrogen. So, in some of the reactions, sometimes once in a while these odd Z elements are also formed and therefore their abundance is quite low. There are some very important reactions which I will show here. Here you have 18 oxygen plus 4 He giving 22 neon, and this 22 neon when combined with an alpha particle, it gives 25 magnesium plus neutron. Why this is important? This is important because this reaction is producing a neutron. You will see that this neutron plays very important role in nucleosynthesis. Similarly, here this carbon plus proton gives 13 nitrogen, that decays into 13 carbon, and that 13 carbon, if that combines with 4 helium, that gives 16 oxygen plus neutron. Similarly, here this 12C plus 12C can also give you 23 Mg plus neutron. Of course, this is energy consuming. It's energetically not favorable. It's minus 2.6 MeV. So, the initial energies are lower and the final energies, rest mass energies are larger, but then at high temperature it is possible. At high temperature it is possible this reaction. So, neutron is produced here, right. So, these are some of the once a while type of reactions which give me more elements, more neutrons. Sometimes they produce neutrons, sometimes they produce these odd A nuclei and so on. Now, this sequence or this process which I described, that explains me the formation of nuclei with that A value less than 56, less than equal to 56 or around that, up to that iron nickel thing, from hydrogen helium to this iron nickel, that we can understand through this nuclear fusion going inside the core of a star. But then in the periodic table we have many more elements beyond this 56 iron. 56 iron is only in 3D in the periodic table, that 3D block in that period. Fourth period you have iron, and after that you have so many elements. You have whole 4D block and 5D block, and then rare earth and actinide and transuranic and so on. How are those elements formed? How are those nuclei formed? They cannot take place through this kind of fusion, because if you remember your binding energy per nucleon versus capital E diagram, it is highest at this 56 iron nickel region, and after that it falls. So, nuclear fusion will not create all those things. How is that done? That is done by a process which we called neutron capture process. once you have certain stable nuclei and if you have neutrons present, then these neutrons can get into the nuclei and form a somewhat higher, heavier nucleus. It's in fact, when neutron gets captured, you do not produce a new element, you only produce a new isotope, but total mass number capital A, that increases. So, this can be one process, but then you do not need that Coulomb barrier penetration, right. So, the best part of this neutron capture is that you do not need that Coulomb barrier, because neutron itself is a chargeless particle and then it can just go and sneak there. So, if you have a regular supply of neutrons, then these neutrons can get absorbed into the existing nuclei to give you a heavier elements, and that is why these neutrons are important. On the screen I showed you that there are certain reactions which produce neutrons. Now, these reactions are important because in the early stages they have produced neutrons, and these neutrons at the later stages can sneak into those nuclei to give you heavier and heavier and heavier nuclei. So, I will stop here, and next lecture we will elaborate more on this neutron capture process and synthesis of elements, synthesis of nuclei heavier than that iron nickel region.